Let's talk about very basic control concepts that we often use in robotics. So we'll talk about PD and PI control. PD stands for proportional derivative control and PI stands for proportional integral control. But before going there, we'll draw a block diagram, and a control block diagram is nothing but a schematic representation of flow of information and decision making. So control block diagram is a simple schematic representation of flow of information and decision making. Okay, so let's draw two control block diagrams, one for PD control and one for PI control, and let's take the example of this controlling a motor that is attached to a robot. So let me go ahead and draw the block diagram. So let's say we have the motor that we want to control, and the motor moves and achieves a certain angle, let's call it theta. And what these controllers are doing is sensing this angle, and I'm going to draw this flow of information of whatever angle is sensed. It goes back to the controller, and let's say there is a desired angle that you wanted to achieve in the first place, and here what is happening is there is a comparison between what was desired and what is actually happening. So you subtract theta d minus theta, so that's why there's a negative sign here, and this is an error of what had to happen and what actually happened. So you can call this signal an error, and this goes to the controller. And if you are doing a proportional derivative control, this will again have two components. The first component is it takes the error and it simply multiplies it by a proportionality constant and then decides how much torque to apply on the motor. And then the second part is the derivative action, where it takes the error and takes the derivative of that, the time derivative of that, and then applies a gain to that derivative. Let's call that kd. And the final control action is a combination of both of these. So you add both of these together, and then this goes as the input signal or the input torque to the motor. And once you put all of this together, this is called a feedback loop, and this helps ensure that the motor is always achieving an angle that you wanted to achieve in the first place. And it's up to the user to choose both of these gains, kp and kd. Having drawn this, now let's think about this a little bit more. What this is really doing is taking corrective actions based on two different pieces of information. First piece of information is how bad the error is, and take some corrective action based on that. The second piece of information is how rapidly is the error changing. Is it increasing at a rapid pace? Then you need to take a stronger corrective action, and if it's not increasing at a rapid pace, maybe you don't need such a strong corrective action. So a simple example would be, let's say you are driving a car down the road and you want it to be at the center of the road, and when your car is drifting away from the center, you notice that there is a certain error between where you want it to be and where you are going, and you are taking a corrective action based on that. That would be a proportional control. The other part of it is, if it's drifting away very rapidly, for whatever reason, then you panic and say, I have to correct back quite rapidly, right? We've all been in that situation. Suddenly it gets out of hand and we want to correct quite rapidly, and that would be a derivative action, right? So this is a very common way to control a motor for a robot. But in some cases, we would also need a different logic. We would need a proportional integral logic. Now, the difference between proportional derivative and proportional integral is this branch, instead of acting based on the rate of change of the error, it acts on the integral of the error. Now, what is the integral? Integral, one simple way to think about it is the accumulated error over a period of time. So it may be that the proportional term is only looking at the error, but over a longer period of time, if things tend to drift, then the integral action will be able to correct for that. So let's draw a quick example block diagram for integral action as well. And I'm just changing the example here. We are still controlling a motor, but instead of thinking of the angle of the motor and the desired angle, let's think of the current in the motor and the desired current. And there's a reason for that, and we'll come back to that later. So I still have a motor, and there is some current flowing through the motor. Let me call it I. This is sensed and sent back to compare with what the desired current needed to be, and this difference is the error in the current. And here there are again two branches. One is Kp and the other one is an integral over time, and this is multiplied by again Ki, and they are added together and goes in as a input to the motor. Now, both of them have their own places. Typically, when you are doing position control or angle control, you tend to prefer PD control, and typically when you are doing current control or torque control, you prefer PI control. Now, interesting thing here is a user only needs to pick these two constants, and in many cases you can also just try out many different values for those constants and figure out which one gives you a good performance. And you don't really need to know what's going on under the hood in the motor, right? So in technical terms, I would say to do this, you don't really need to have knowledge of the dynamics of the system that you're controlling. Of course, if you do, then it can help you pick these gains in a smarter way, but even if you don't, you could still do a reasonably good control by doing this. So just like when we get into a new car, we don't really need to know what kind of engine it has, how much power it has, what acceleration it will have, and what mass and inertia it has. We can just figure out, oh, if it's drifting to the right, I need to correct to the left, and so on and so forth. Just by doing this is able to achieve fairly good control for most situations. As you get to higher level of complexity of tasks in robotics, you would use higher level of complexity in control, but these are still very common, and at the innermost loop these are still very, very, very widely used. So that's it. This is all you need to know to get started with control for robots.